So a while ago, I built this little VU meter using 8 op amps as comparators, and it's very responsive. And basically, this is a type of analog to digital converter that is called flash ADC. So this is, I said it at the time that it was an 8-bit, but it's really not 8-bit. It's very pleasing to the eye when you're using it as a peak level detector, a VU meter for music. However, it only goes between values of 1 and 8. So basically, if you think about it in binary, that's only a 3-bit analog to digital converter. In order to implement this, I used 1 op amp for every level, so a total of 8 op amps. If I wanted to make a true 8-bit analog to digital converter, I would have to use 256 op amps in order to make it happen. Now that becomes a little bit unruly. It would be fast, but it wouldn't work well. In order to make a fast analog to digital converter but not require as many op amps, we use a technique called successive approximation. And while it's not as fast as flash ADC, it can still be used very quickly and give a very good approximation of the analog input voltage. And the way this works is basically with each step, a successive approximation is made on the input voltage with the digital output and is stored and output at the end. A couple of weeks ago, I made a video about the AD0804 analog to digital converter, and this is an 8-bit analog to digital converter that uses successive approximation as its algorithm. And this chip can function at 1.2 megahertz, which is pretty darn fast. And here you could see an input voltage going into the input, and the binary digital output on the lights. So today we are going to make our very own successive approximation analog to digital converter. So a rudimentary sort of block diagram of how this process would work with a 4-bit digital or analog to digital conversion with all the necessary pieces is right here. So you start out with this basic clock signal, and what it's doing is it's clocking in a 1. The data input to the shift register, the 595 shift register, is a 1, and so it's basically propagating the 1 all the way through. So if you look at the output of Q0 of the shift register, it's just 1 the entire time. This gets triggered on the second clock cycle. This Q3 or Q2 gets triggered on the third clock cycle, fourth clock cycle, and at the fifth clock cycle is a reset signal, which resets the shift register and clears it, and it resets the D flip-flops, and it resets and allows the latching of the data that you've accumulated. The way this works now here is with the D flip-flop. At the reset, at the beginning, all the D flip-flops, the data is all 1. And so these are all set to 1, which is equivalent to a 16, 1, 1, 1, 1 in binary. What happens is, since these are not clocked in and only this one is clocked in with the first output, this becomes this essentially to the digital to analog converter, since this 1 has not been clocked in yet, is 1000, and so 1000 on a 5-volt circuit on the digital analog conversion will be 2.5 volts. So if your input voltage, if your reference voltage is less than 2.5 volts, what happens is the comparator puts out a 0, because if this is less, it's 0. If it's greater, it goes high. And so if it's less, for instance, the output of this is 0, and what happens is this 1 gets converted to a 0. and stays that way. Now it's 0, 1, 1, 1. Now, if on the second clock cycle, the second flip-flop is activated, so the 1 that's in there already is clocked in, and so now, since this is a 0, it's going to be 0, 1, 0, 0, and so it tests the second bit, and if that value is higher or lower, that will change all the data to the appropriate values. And so let's say it's greater, then the 1 stays, and then it continues and until the last flip-flop is changed. As these outputs of the flip-flops are changed to their appropriate values, the shift register and the Q flip-flops, in order to get them to a latchable form of storage, are put through AND gates along with the shift register outputs at each appropriate level in order to store the correct bit in the correct location. And so I used AND gates for that, because one of these has to be high and this has to be high in order to get it to go there. And at the last clock cycle, the 5th clock cycle, after all the bits are set, is a reset signal. So once again, all of the D flip-flops are reset to a value of 1. So they're set. The shift register is reset and cleared to the beginning, and the last output of the signal is a latching signal for your latch chip. In this case, I used a 74HC 574 to latch it, but any latch chip would do. So that's how the rough version of the schematic. So the components that we need for this project are a clock, which is a 555 timer, a shift register. I'm going to use the 74HC 595. A set of D flip-flops, 1 flip-flop for each bit resolution. Then we need a comparator, which is an op-amp, and basically you need it to make the decision and compare values of the analog voltage to the reference voltage to change the flip-flops. Then you need a digital to analog converter, which is just an R2R ladder. You need a handful of AND gates. And at the end, you need some way to store the output in data in a latchable storage register. So I have here a 555 timer on the left side, and that is driving this 74HC 595 serial in, parallel out shift register. Let me turn this off so everybody can see. And basically, that circuit is serially turning on all of those LEDs, and then it resets. The reset mechanism is basically a transistor or a resistor going to the base of this transistor, which is wired as an inverter. And basically this goes off when this pin goes on, and there's 1 blank clock cycle, and then that triggers the master reset of the 595 shift register. And so when I turn it on, and I just have the LEDs there. They're really bright. I don't have enough resistance on them, but they're doing the trick. So that works. So now the outputs Q0 through Q4 of the shift register, or Q3 of the shift register, are the clocking signals of the 4D flip-flops in this 4-bit version of the ADC. And also they trigger the AND gate in order to, of the subsequent flip-flop, in order to provide data to the digital to analog converter. The output of the digital to analog converter, which is the R2R ladder, gets set as the reference voltage in the inverting input of the op-amp comparator, and the non-inverting input is the reference voltage, analog voltage that's being measured, and the comparator outputs a 0 or a 1, and that gets clocked into all of the flip-flops, changing all of them, but the only ones that get clocked in are the ones that are actively being clocked by the timing of the shift register. The outputs of all the flip-flops, the cues, are all put into a storage register, which is latched at the end of the whole cycle, and then the cycle repeats itself. So using that circuit and an op-amp based comparator right there, I have this set of 4 flip-flops and 4 AND gates and a digital to analog converter using an R2R ladder. I have here a successive approximation analog to digital converter, which is only 4 bits, but this is just proof of concept, so it could be expanded beyond that. So now, let's see if I lower the reference voltage, the analog voltage to be measured is in the blue curve, and so if I lower that, it approximates it. Let me lower it even more. Now let me increase it. It's a pretty close approximation. And I have the clock that's clocking it very slow, so every couple of seconds we have an approximation. So now I replace the 1 microfarad capacitor on the 555 timer that's clocking all of this in just to speed up the circuit. And let's test it out and see how it approximates. So now the blue curve is still the reference voltage, and that's controlled by this voltage divider potentiometer. It's 100 kpot. And as you can see, that last little signal where it gets to the bottom, you can see the process going. Now let's see if I can speed it up or increase the voltage. Yep, it always ends up there. And you can watch the yellow tracing successively approximating each time. I'm going to go all the way to the max here, and it goes to the max. One last thing on this analog to digital converter, if I increase the reference voltage, which is the blue curve, to max, the yellow tracing can only go high as 4 point, this is measuring at 4.76 volts. But if you think about it, a 4-bit analog to digital converter has, let me stop it, has a maximum of 4 bits. So if each of those bits is set at 1, the first bit, according to the digital to analog converter with the R2R ladder, is half the voltage. So half of 5 volts, which is the VCC, is 2.5. And then the second most significant bit is 1.25 volts when it's set. And then the third bit is, what's it called? 0.625 volts, and the last one is 0.3125. So if you add all those together, you get about 4.7 volts, 4.68 to be exact. So that's the maximum with 4 bits set at all set to 1. So a binary value of 15. So that is the reason why it's never going all the way to the 5.1 volts. However, at 0, when all those bits are set to 0, if I turn this down, the reference voltage all the way to 0, it approximates to 0 very well because all the bits are 0. So when all the bits are 0 at the exact time when this is stopped, it gives you a minimum of 0 volts. So that's a lot more realistic. I have here 4 LEDs for the 4-bit analog to digital conversion. So far, this is what the conversion process looks like. The yellow curve is the reference voltage, and the blue is the approximation going into the comparator. That's the digital to analog conversion according to this R2R ladder. So I have here a CD4029 binary counter. This is a temporary storage because it's presettable. And what I'm going to do is I'm going to slowly increase the voltage here on my voltage divider and watch the bits go up. That's at 1, 2, and slowly go up. I'm almost at the halfway point. And that should be max. So basically I'm using this counter, which is presettable, as a successive approximation register to store the bit values in order to display them in LED format. Also, as you notice, the speed on the clock is much higher now. It's 100 hertz. I changed out the resistors and capacitor on the 555 timer in order to speed up the process slowly, in order to prevent the LEDs from just blinking slowly to life as I do the conversion. So I got it up to 10.8 kilohertz now. Here's the successive approximation register ADC in action. Let's see the lights go on as I turn the reference voltage. Also, I'm no longer using a CD4029 binary counter that's presettable as my storage for the output. I actually got a proper latch chip, which is a 74HC574, and that's in the final schematic. Also, to get it up to that high of a frequency, I had to use a set of smaller resistors and a 1 nanofarad capacitor in the 555 timer. So I'd say that this 4-bit analog to digital converter works fairly well. And the beauty of this design is that it is scalable and can be scaled up to whatever bit resolution value you want. So in this case, why not make an 8-bit ADC? We just need to double the number of components that we use. So here's the final product. This is a successive approximation analog to digital converter. I have it here running at 6.1 kilohertz, and I have 2 tracings up there. And let's watch as I adjust the volume or the voltage divider knob. That's at 2.5 volts, 2.7. Let's zoom in on it a little bit. You can watch the approximation. Let me put this down a little bit and this down a little bit. No, the scale is different. Let's change the scale. I was wondering why they weren't matching. Here we go. Approximates it pretty well. 8-bit ADC. Thanks for watching. So a couple of final points here. So every time you scale this up to a higher resolution, when I went from 4-bit to 8-bit, I not only doubled the number of components, but I divided the speed at which it functions in half. So you can increase the clock rate to a point, but it still slows it down. So in my case here, if I want to make a 17-bit ADC that's custom with parallel output, I'm going to slow the clock speed down by 17 times. And in case you guys are wondering, the cost of an ADC that's higher resolution than 16-bit with parallel output is upwards of $100 to $200. So this is totally worth it if you're going to do your own for a custom value.